We're going to continue talking about derivatives as functions, but now we're going to specifically talk about graphing them. How to be able to graph the derivative function? Well, what we're going to do is focus on the fact that the derivatives are nothing more than the rate of change or the slope of the tangent line. This is a pretty easy example to start off with, but a lot of students have trouble with this. If I have a line segment, the slope over that line segment is constant. Therefore, the tangent lines are actually the line segments themselves. Let's look at this graph below -3. This is the tangent line of the graph less than -3. If I just read that slope off of the graph, that is, I find delta y over delta x, let me zoom in on that. It looks like my change of x, that's a +1, and the change in y equals -2. Therefore, the slope, or delta y over delta x, is simply -2. If the slope is -2, I graph the horizontal line -2. That is, no matter what x is, y is equal to -2. Let's look at the next portion. Well, that slope, that's simply 0 between -3 and -1. And I'll graph it like that. My next section, let's look what the slope is there. I get delta x is 7 and delta y is 7/2. So if I put delta y over delta x, I get the slope of 1/2. And this is a positive slope. Now I have one more line segment, and this looks like a negative slope. For the 2 points I've chosen, delta y is -7/2 and delta x is +7/2. That means the slope at this point is -1. So this looks great except for 3 points. What should I do with these 3 points? I really can't talk about a tangent line. Let's take this third point. I could have a line like that. I could have a line like this. There is not one single tangent line at a point where I have a sudden change of slope. So I'm going to be able to say this. The first derivative of f at -3, -1, and 6 are undefined. There is no derivative at those points. So to indicate this on the graph, I'm simply going to put open circles. That means at those points, there is no derivative. Let's do another graph. Okay, here's an example with asymptotes. And here's the checklist that I'm going to be going through. First of all, there are no line segments, so I don't have any easy sections to do. I now need to find when the slope of the tangent line equals 0, and I see that only once. I see that right here. So I'm going to mark that point as equaling 0 on my graph of the derivative. Where there's an asymptote on the function, there's also going to be an asymptote on the function's derivative. So I'm going to break this up into 4 sections. And I'm breaking this up either by an asymptote as a boundary or where the tangent's equal to 0 as a boundary. The next thing I'm going to do is in each section mark whether the slope is positive or negative. That means whether or not the graph of the derivative will be above the x-axis or below the x-axis. In section 1, it's a negative slope. In section 2, it's also a negative slope. We have a positive slope in section 3 and a negative slope in section 4. So now that I know what the sign, S-I-G-N, of the slopes are, I can go ahead and start graphing this. It looks like in section 1, I start with a slope that's about equal to 0, and then it gets infinitely negative. So it should look something like this. In this case, it almost looks like my original graph. Okay, in section 2, I start off with a slope that is very, very negative. And let's draw some tangent lines. So it starts off really, really steep in terms of a negative slope. And I'm going to warn you, you're going to be very tempted to draw the slope like this because it's very, very steep and then it gets to 0, but it's a negative slope. So we're not going to do this. Instead, we're going to have an infinitely negative slope going to 0. In section 3, it goes from 0 to a large slope that is positive infinity. Again, you're going to be very tempted to do this because it's a very, very large slope and it goes to 0, but it's a very, very large negative slope. So it will look like this. Graphing derivatives takes a while to get the hang of. Follow these steps. Look for line segments, find out when the slope of the tangent line equals 0, break it up into sections, and check the slopes in each section. And before you're done, make sure if everything's negative in section 1, if everything's negative or below the x-axis in section 2, above the x-axis for section 3 and below the x-axis for section 4. I'm going to make two statements without proving them. I'm going to say that if a function is differentiable, that implies it must be continuous. If a function is not continuous, then there is no derivative at that point. It is not differentiable. But, and this is a big but, continuity does not necessarily mean that a function has a derivative, that it's differentiable. So, what does this mean? If I tell you the derivative is defined, you know it's continuous. If it's not continuous, there is no differentiation at that point. However, we've already come across one example where a function was continuous, but there wasn't a derivative at that point. And that was our very first example. Corner points where the derivative quickly changes, those are not differentiable. Those don't have to be straight lines. It could look something like this. Anytime you have an instantaneous change in slope, there's no derivative at that point. Let's look at one other example where a function does not have a derivative. Two other situations are if I have a cusp or another function with a vertical tangent line. So if I have a vertical tangent line, this is not differentiable. So what are my three cases? If it's not continuous, if there's a corner point, or a vertical tangent line. In those cases, the function is not differentiable at that point. Let's do a quick example. Let's say I had a function like this, and I wanted to find its derivative. In the first section, I have a constant because this is a line segment and it's a positive slope. But at that point, where it jumps up to the curved line, there is no derivative. In section 2, that's a negative slope, and it gets infinitely large. In section 3, it's a positive slope. It starts out as infinitely large, and then it goes to 0, because this is a vertical tangent line. However, in this case, because there is no point, because that is not continuous at the point where the vertical tangent line exists, there is no derivative there, so we're going to mark that as a open circle. And then in section 4, it's a positive slope going up to positive infinity. And I can explicitly say that f prime of 0 is undefined, as well as those other 2 points where there's just open circles.